Hi, we are gonna get started very soon. I think we'll actually get started now. Um, and today we'll just be covering again some geometry, and we'll be covering content on polygons, quadrilaterals, cyclic quadrilaterals, and some circle properties. And like I said before, if at any point you sort of want to ask any questions, just feel free to go ahead. There isn't a lot of us as either, so yeah, just like feel free to ask any questions you have in mind. Um, I'll quickly cover this. If you want to find course content after class, you can either find it on the email attached. We'll also, I guess, post the videos onto YouTube so you can have a look. I think it hasn't necessarily been within 2 days after class, but we'll work on that. Okay, so polygons. So who here knows what a polygon is? Also, if you guys are happy to like turn on your cameras, that'd be also really nice. But who here has an idea of what like a polygon is? No one? Yeah, okay, well, okay. Yeah, a many-sided shape, yes. I see Lol has her hand up. Do you wanna give it a shot as well? About what you know about polygons?
It's just a shape with sides.
Yeah, yeah, like basically, right? So I think both of what you guys have told me is what you largely think of when you think of polygons. And a polygon is basically the formal definition is a two-dimensional closed shape formed by straight lines, right? So yes, it can be like a many-sided shape, but more specifically, it should be like a closed shape formed by straight lines. So that's just a rough definition. And here in the corner, we can see there are a lot of examples of polygons, right? And they're like of all types of random shapes. We can see rectangles, we can see triangles, we can see some like weird crossing over lines and things. Yeah, so all of these are closed shapes that are formed by straight lines, right? So they're polygons. And okay, we'll talk briefly about some characteristics of polygons. So does anybody know anything about either maybe the angles inside a polygon? What would like the angles inside a triangle be? Like the interior angle sum of a triangle. Yeah, yeah, go ahead.
Isn't there like a formula or something to find out the total interior angles for like those polygons? Or is it?
Yeah, exactly, right? Like, so there is a formula, and let's see if we can actually like find the pattern or the formula somehow, right? So what is the interior angles of what is the interior angle of a triangle? Feel free to like type it in the chat or like shout it out. Yeah, 180, right? So this would have an interior angle sum of 180. What about a rectangle or like a four-sided shape? What's the angle? Yeah, 360. Okay, cool. I'm not sure if okay, there's a five-sided shape here. What do you guys think would be the interior sum of this one? Oh, like a regular pentagon or like some sort of yeah. So what about a five-sided shape? Yeah. Exactly, right? So for a five-sided shape, the interior angle sum would be 540 degrees, right? So do we start noticing a pattern, right? So this is a three-sided, this is four-sided, this is five-sided. What's the relationship between like the angles? How much is it increasing each time? Like we increase the number of sides. Yeah, exactly, right? So we can see that from 180 to 360, we're adding 180, right? And 360 to 540, we're also adding 180. So this sort of makes us think, okay, maybe every single time we increase the number of sides by one, maybe the angle has to increase by 180, right? And actually, this is true. And like one of our students were able to tell us, the formula for the sum of the interior angles of an n-sided polygon. So n would just be the number of like corners it has, the polygon, or like the number of sides it has. The interior angle sum is given by this formula. It's n minus 2 times 180, right? And if we test this out for, say, like a triangle, for a triangle, obviously our polygon has three sides, right? Because we could we could count if we wanted to, but there's not too much to count. One, two, three, three sides. So n would have to be equal to 3. If we substitute n equals 3 in, then n minus 2 would be 1 times 180. 180 would just be 180, right? Which is why the interior angles of a triangle is 180 degrees. I see uh, Kinsley has their hand up. Do you have a question or like a comment you'd want to make?
Is like n minus 2 the number of triangles that you can make in the polygon?
Oh, well, yes, that is also a very, very good point. Exactly. So, what Kinsley has brought up is say we have a five-sided shape. How many, like, if we start from one corner, how many triangles can we make, right? And exactly, Kinsley suggested, we could actually make three, right? And in any case, like for an n-side polygon, we can make n minus 2 triangles from starting from the same shared one corner, right? And now, if we think about it, these triangles each have an interior sum of interior angle sum of 180, right? And now there's n minus 2 of these triangles that can, like, we can partition or we can split our polygon into n minus 2 triangles. So that is also like a really, really good way to explain why this formula works, is that we can partition or split our polygon into n minus 2 triangles. Each of these triangles is 180 degrees. So if we add them together, sort of that's just why it would be n minus 2 times 180. Does that make sense to everyone? Yes, no, maybe. Okay, perfect. Yeah, so that's also a really good way to, like, if you forget the formula and you want to like re-remember it, you can think about it like this. Okay, so another point that comes up is does everybody know what a regular polygon is? Would you define a regular polygon?
Is it a polygon
Is it a polygon?
that
Yeah,
has equal sides and equal angles?
yes, exactly. Right. So for a regular polygon, say it's a triangle, it would be an equilateral triangle, so all three sides are the same, and then 60, 60, 60. For a four-sided shape, or a quadrilateral, it would have to be a square, right? All of the angles are 90 degrees and they're all the same side length. And then you have your regular pentagons and so on and so forth. Yeah, so they have to have same interior angles, same sides. Okay, length. Okay, cool. And then the following result is that the exact size of each interior angle is going to be n minus 2 times 180 divided by n. And I think this follows quite naturally from this formula that we talked about over here, which gives us the total angle sum inside a polygon. Well, now, if you think about the definition of regular polygon, all the interior angles have to be the same size, right? So you have n angles on the inside, so you're just dividing the total angle sum by n, and you get the size of every interior angle, right? And we could test this out for a triangle, or like a square, and we notice that, yes, this is indeed true. Any questions? Does everyone want to try it out actually, or do you all see sort of how it works? Yes? Okay. Okay. I'm gonna take that as everyone sort of understands what's going on. Okay, then let's move on. And then the next section we're gonna be talking about is quadrilaterals. Can somebody give me like a definition of a quadrilateral?
Four-sided shape.
Yeah, exactly, right. So a quadrilateral is basically just a type of polygon, and specifically it has to have like four-sided. It's a four-sided polygon, right? And some special types of quadrilaterals that you guys might be familiar with are the parallelogram, rectangle, rhombus, square, trapezium, and the kite. So, does everyone know all these shapes, or is there one that you think like you're not too familiar with that we could talk about a little? Yes, no? I think I will talk a little bit about the trapezium. Um, which is basically that, okay, I think this diagram is a little bit misleading, but the idea is that for a trapezium, you just need one pair of parallel lines. And for an isosceles trapezium, these would all, the other sides, the non-parallel opposite sides would also be equal length. But for a normal trapezium, the only condition is that you have one pair of parallel lines, right? And parallelogram, it's that you have two pairs of parallel lines. Rectangle, I think we're probably a little bit more familiar with. Yeah, and okay, and a kite is sort of where we have that symmetry. And rhombus, does everyone know what a rhombus is? Rhombus? Okay, we'll talk about. Okay, yeah, so basically a rhombus is very similar to both a square and a parallelogram, sort of. But the idea is, yeah, it's a t okay, so a square would be a type of rhombus, but all the sides have to be the same length, and you also have two parallel pairs of sides, is basically what a rhombus is. Yeah, so a slanted square is a pretty good definition, or like a way of thinking about it. A kite, is basically, you can think about it as you have two pairs of equal length sides, but these equal length ones have to be sort of adjacent to each other, right? So for a kite, you can sort of split your kite into two isosceles triangles, which is something we talked about in our last geometry session. But that just means you sort of have here and here are your two isosceles triangles, and you sort of put them together. And what I meant when I said there's sort of a line of symmetry is if we took the line down here, then we have a line of symmetry, right? So that's basically a kite shape. Okay, and then square, rectangle, I think we're more familiar with parallelogram. Also, like I just said, two pairs of parallel lines. Okay, let's keep going. Um, Okay, so I think we're more or less, we sort of know what quadrilaterals are, but what about a cyclic quadrilateral? Who knows what a cyclic quadrilateral is? Yeah, so a cyclic quadrilateral means that, okay, so what does first the word cyclic tend to mean sometimes? So cyclic usually just means something to do with like a circle. And quadrilateral, we know, is obviously like a four-sided shape, right? So together is what it means a cyclic quadrilateral is a four-sided shape that is able to fit in a circle such that each of the corners sort of sit on the circle, right? And we can look at this in a diagram. So a cyclic quadrilateral is a quadrilateral where all four vertices or corners are lying on the circle. And we can see what that would look like visually. It's that we can see the four sides of the shape rest perfectly on our little circle, right? Um, and for a square, this is true. For a rectangle, this is also true. And for a bunch of other shapes, we find out this is also true, right? But we have to, I guess, prove it. And we can see some proofs or like some explanations or conditions for cyclic quadrilaterals a little bit later. So what we should take away is that first, not all four-sided shapes are going to be able to fit perfectly into a circle, or we cannot be like all perfectly inscribed within a circle, and only certain quadrilaterals can. So if we're looking at this diagram A, B, and C, which ones would you say is cyclic? At least as we sort of see it.
B and C.
Yeah, exactly, right. And that's because all four of the sides of the quadrilateral are resting really nicely into a circle, right? And that's what sort of cyclic means. Okay, cool. Let us move on to talk about okay. We'll first talk about the circle, and then because we've learned a little bit about quadrilaterals, after we learn a bit more about circles, we can put them together and we'll have a little bit of a better understanding of what a cyclic quadrilateral is. So let's first touch on some circle properties, right? So a circle, as we should probably all be familiar with, is this like a round shape which has a constant like radius, right? Or a diameter. Um, so basically, in our circle, we have a center, and from the center, each point on the circle is an equal distance from this center. And this distance is what we call the radius, right? Is everyone familiar with that? Yeah? Okay. So yeah, circle has a constant radius, and usually it's like radius is denoted by r, and 2r is just usually known as the diameter, which is basically this line, which is 2 times the radius. It's just a line that goes from one side of our one point of our circle to the like diametric opposite point on our circle. So that would be our diameter. Some other words that you'll come across in terms like when you're talking about a circle would be a sector, right? So a sector I feel like comes up a little bit less often, but if you're talking about like a sector of maybe like a cake or a pie, you're sort of talking about like a slice of it, right? So that just means you're starting from the center of our circle and you take a slice, right? This would be the sector. Often you might hear something like, find the area of this sector of the circle or whatever. So that traveling from the center to the edge of our circle would be like creating a sector. Another one that you'll come across is segment. So segment is it's also sort of like I think okay, let's talk about chord first. So chord is basically just like a line. Like right, we take a line that cuts from one side of our circle to another point on our circle, and that's what you have as a chord. A segment is basically the edge of your circle and a chord. It forms sort of an area, right? So that becomes your segment. I think segment doesn't come up a lot, so I wouldn't worry too. Yeah, Kinsley?
Is the diameter a chord?
Yes, you could say so the diameter, if it's like a line across, yeah, it would also be a chord, right? Because it sort of satisfies what we're talking about in terms of a chord. Okay, anything else? Okay, perfect. And then, ooh, okay, secant doesn't come across, you won't come across that much. Tangent we talk about later, so I'll save it. But okay. Circumference. So circumference, most of you might have heard of. It's basically just the line that actually creates the circle, right? So it would be this bolded black line over here. It would be just your outer side that forms your circle. So in a circle, there's one side, right? And that's the outside ring, and that would be your circumference as well. So, what are some formulas that we know about the circle that you guys can think of? Anyone? Yes. Okay, perfect. Yeah, so exactly. So for the area of a circle, we use the formula pi r squared, right? And r stands for what we talked about, the radius. So we're trying to figure out what the area of a circle with radius r is. The formula is just pi r squared. And the circumference would be 2 pi r, right? So that would just be working out what's the length of that like curved edge of our circle. Okay. I see a few more formulas. Pi fra- okay. I think the other ones,
Pi d squared over 4.
yeah, so I think that's the same thing. That's the same thing as our pi r squared. So I wouldn't worry too much about that. But yeah, so these are the two very, very common formulas you'll come across, and I think we should all be somewhat familiar with them, right? And now we're gonna talk about some things that we might be a little bit less familiar with, right? So one formula or one theorem that we're given is that if we start from a chord that is our diameter, we start from our diameter and we draw a triangle, I guess, or an angle to the edge of our circle, like this, like we have in our diagram, well, then we're given that this angle that is created with the base of the diameter is going to be 90 degrees. So it's like if I did this would mean this is also 90 degrees. So any angle that I create from the diameter to the edge of my circle is going to be 90 degrees. Does that make sense to everyone? Okay, now can we think of why this might be? What might be like a reason, or how could we prove that this is true? That like whatever point I choose, as long as I connect it from the diameter, it's always going to be 90 degrees. It's like, why is this true? Cut it into two circles from the center to the point on the circumference. Okay. Yeah. So exactly. One of at least the probably easiest explanation I know is probably similar to what one of our students have told us. We can draw a line from our center to that point that we chose on our circumference, right? And then what do we know about each of these lengths? What is special about them?
They're all the radius.
Exactly, right? So we can all denote them as R. And we don't really care about what exact length this R is. We just want to know that, well, all three of them are equal, right? So that would mean this length is equal to this length is equal to this length. I will add some letters to my diagram. So let's say I write the triangle as ABC and the center is O, right? Well, that would mean that AO, BO, and CO are all the same length. Now, okay, if we're looking at this shape and this shape, what is special about these two shapes? What type of shape are they? Exactly, right? So they're isosceles triangles. And what do we know about isosceles triangles? At least the angles of isosceles triangles? Exactly. So the base angles have to be equal, right? That is, I guess, what the definition of an isosceles triangle, and it's actually really, really helpful in this case. So I don't know what the angles are, but I can denote them, say, as alpha. And okay, so this is AOB is an isosceles triangle, so I know the base angles, these two base angles are equal. BOC is also an isosceles triangle, so I can denote them as beta, right? So we can sort of see that their base angles are also equal. Now, okay, now going back to what we know about the interior sum of a triangle. What do we know about the interior angle sum of a triangle? So after we sort of do this, it becomes more of like an, I'd say, algebra problem than really anything to do with geometry. Yeah, exactly, right. So we know that inside any sort of triangle, the interior angle sum is 180 degrees, right? So if we're looking at triangle ABC, interior angle sum is 180. But what actually are the three angles within triangle ABC in terms of alpha and beta? What would that actually be? Yes, exactly, right? So if we look at the three angles, and first we don't actually know, just so you know, we don't know what it's 90 degrees yet, we're trying to prove that. We could look at the three angles and we see that, okay, one of them is alpha, one of them is beta, and one of them is alpha plus beta, right? So that would mean that alpha plus beta is equal to 180. Now, if we sort of treat this as an algebra problem, that becomes 2 alpha plus 2 beta is equal to 180. And we divide both sides by 2, and we get alpha plus beta equals 90, right? And now if we look back at which angle is alpha plus beta, well, this angle is alpha plus beta, right? So this green angle is alpha plus beta, right? And we know that this is going to be equal to 90 degrees. So that's one way you can sort of show that the angle in a semicircle is 90 degrees. Do you have any questions? Perfect. Let's keep going. Okay, and then another theorem that we have is that the angle at the center of a circle is twice that of an angle at the circumference, which is subtended by the same arc. So this just means that, say we have some random angle over here, and okay, and then we say we say it's theta, right? We just name it theta. What this theorem tells us is that if we go from the center of our circle again, we take the center O, and we use the same sort of same arc, but we draw this angle. Then it would be 2 theta. Does that make sense? Just what the statement is talking about? Nope. Oh, wait, no, that was from before, sorry. Um, yes. We will talk about how to prove this or like why this is a little bit later. but just does this make sense so far? Okay, perfect. Yeah, nice. So, okay. Now does anybody or can anybody think of why this might be or like a proof for this? I would say that for all of these more fundamental circle theorem proofs, a lot of the time you're considering isosceles triangles, and like you can simplify the question down to isosceles triangles just because of your conditions with the radius of a circle. Yeah, exactly. So, as Elizabeth has told us, that we might consider drawing this line. We might, because this line would help us form some isosceles triangles, and that can be really helpful, right? So we know this angle is theta. The big angle that it's theta, but we also know that this big angle can be split into like to be part of two isosceles triangles. This one and this one. So if we say this side of the angle is equal to, I don't know, a alpha, when we say this side of the angle is equal to beta, then first we know that alpha plus beta equals theta. What else do we know? I don't want to spoil anything for anyone who's giving it a go. So do we have any ideas that we can talk about? Or I might give you guys maybe like 1 or 2 minutes to think about it. Yeah. Okay. So we've got some really great ideas. Uh, is anyone is anyone still trying the problem? Like we're trying to give it a shot to prove it. I don't want to like spoil everything without giving you guys like the time to think, because I think that's really important. Um, so let me know if you're still thinking about this problem, or else I will start talking about it. Okay. Then I'll start talking about it. Okay. Cool. Yeah, exactly. As I think David talked about. We have two isosceles triangles, right? And again, we know the base angles of an isosceles triangle are equal, so we would know that this angle is going to be equal to alpha, right? And similarly, we could say that this angle would be equal to beta, right? Now, what would this angle over here be equal to? I don't want to... Okay, I'll use another color, blue. So what would this angle, the third angle of our isosceles triangle, be equal to?
180 minus 2 alpha.
Yes, exactly. So it would be equal to 180 minus 2 alpha. And what about this other angle over here? The green one. Everyone just feel free to like shout things out at this point. Like I don't think there's too many of us, so it won't get too messy. Yeah, 100%. So 180 minus 2. Oh, I wrote beta here, but it's supposed to be alpha, sorry. Okay, 2 beta. Yeah, okay. So we know the sum then of the blue angle and the green angle would be, okay, so 360 minus 2 alpha and 2 beta, right? So the sum of this entire black angle over here, right? Now, what do we know about the entirety of like a whole revolution around a point? How many angles is that? Or how many degrees is that? Yeah, exactly, right? So if we're going around a point in one entire revolution, it's 360 degrees, right? So that means if I were to draw the whole circle over here, that would be 360 degrees. So that would mean this, I don't want to confuse anyone with using too many colors, but bear with me. That this angle over here plus this black angle should be 360, right? So that would mean 360 minus 2 alpha minus 2 beta plus let's say this angle, I don't know, is x plus x should be equal to 360, right? So that would mean that x has to be equal to 2 alpha algebraically. It has to be 2 alpha plus 2 beta, right? Does that make sense to everyone so far? I have introduced like a lot of variables, which is a little bit annoying. I'm sorry. But is everyone following so far? So when I talk about x, I talk about this angle over here. Yeah, so I just named it randomly, x. So we know that x plus the rest of the angle around that point, the center point, is going to be 360. So hence, we know that this plus x is going to be 360. And if we do a little bit algebra, we can cancel out the 360s. And then we find out that x has to be equal to 2 alpha. Oh, I should use gamma. I could use gamma. Um, I chose to use, if you want, I can use gamma. Gamma is gonna be 2 alpha plus 2 beta. And that would just mean, if we recall back, alpha plus beta is equal to theta. So then gamma has to be equal to 2 theta, right? Does that make sense to everyone? So that's how we prove that indeed, this angle has to be 2 times of what the far angle, or like the angle on the circumference is. Does that make sense? Can I try to get a response from everyone, just so I know? Okay, perfect. Um, okay, then I will keep going. Okay, cool. So that's basically how you prove it. So just to reiterate the statement again, it means that the angle at the center of the circle is twice the angle at the circumference when subtended by the same arc, right? So both of these angles have to be from the same arc. They have to be the exact same sized arc. Okay. Now, these two theorems that we've talked about are theorems that you don't have to prove in when you're trying to do a problem. You usually don't have to prove these. These are well-known enough theorems. You just need to be able to like state them. So yeah, so as long as you remember them well, they can be very, very useful. And I think for this next problem, the theorems that we've already talked about are actually going to be also very useful. And this theorem states that angles from the same arc are equal. So it means that the angle subtended by the same arc, or the same lengthed arc actually, same lengthed arc are equal. Now, how can we prove this? So that just basically means if we're taking AB as our segment, it means that this angle and this angle, both subtended by the arc AB, are going to be equal in size. So how do we think we can prove this? And try to think in terms of what we talked about before. Our two former theorems that we've talked about or mentioned. So let me know when you have any ideas or when you guys want to start like talking about it. Anyone? Anything? Yeah, we want to start talking about it. Sure, we can definitely do that. Is anyone still trying the problem and wants a little bit longer? I'm gonna take that as a no. Okay, yeah, let's start talking about it. So I will just clear up my diagram a little bit to make sure it's a bit clear. So first, what I might think about doing is, so just imagine, obviously it's not already drawn onto the diagram, but I would imagine where the center is. Not just label my center O, right? Because the circle, a lot of the time, oh, and not to be confused, it doesn't necessarily have to be on the line, it's just some random point in the center. And if we connect actually the A to O and B to O, and we say this angle is theta, what do we know about the angle AOB? From exactly what we just talked about. So remember that angle at circumference is a half of angle at center? Yeah, exactly. Yes, so it would be 2 times theta, right? This is exactly what we were talking about with that angle at center and angle at circumference thing, just above. So the angle at their circumference should be a half of the angle at the center, or and vice versa. It should be 2 times at the center. So we know that the angle AOB is going to be 2 theta, right? Now, if we sort of think about the other line, other point C, right? We can use our argument from our theorem above again, right? We know the angle at the center is going to be 2 times the angle at the circumference. So what would this angle ACB have to be? Theta. Yeah, exactly, right? Because we should remember that whenever we are on the same arc, the angle at the circumference should be a half at the angle of the center, right? So both of these angles, ADB and ACB, both have the same angle when we draw the angle at the center, right? Both of them have it at like this, right? So they actually have to be the same size. Does that make sense to everyone? Perfect. Yeah, so as long as you know this condition from above, it's really not that bad um, to do these problems. Okay, cool. Let's move on then. Okay, so now the angles from the same arc. So another useful result is that the opposite angles in a cyclic quadrilateral are supplementary, or they add to 180 degrees, right? So we've talked about a lot about circle properties. Now we want to sort of relate this back to what a cyclic quadrilateral is, right? And remember, a cyclic quadrilateral is a four-sided shape that fits perfectly, or like can be inscribed inside a circle, right? So A, B, C, D in this diagram here would be a cyclic quadrilateral. Now, one very useful result is that for a cyclic quadrilateral, the interior opposite angles are supplementary. That means the opposite angles in your quadrilateral should add to 180. For example, if I take these two angles, then DAB plus DCB should be equals to 180 degrees, right? And this must be true for a cyclic quadrilateral, and it is always like if it is true, then our quadrilateral is always cyclic. So it's sort of like an if and only if statement. Okay, but not to worry about that so right now. Let's just try to prove why opposite angles in a cyclic quadrilateral might have to be supplementary. let me know if you guys have any ideas. I think this one you want to be using what we talked to the theorem we talked about over here. Just had the angles from the same arc equal. And it will really help in trying to prove this statement. Anyone got any ideas? I think like once you guys see how it can be done, you guys are gonna be like, wow, okay, I should have seen this. This is um pretty simple. So yeah, so I think my clue would just be to try to use the result that we proved just before, right? So look at the angles that we're trying to prove are supplementary or add to 180, and then think about how you can sort of maybe find equal angles, and then sort of think about what are the conditions there. If I move one equal angle to the other, how can I think about it? Let me know if you guys have any ideas. Anyone? Or does anyone want to share maybe an idea they have? They don't have to like, or like just make any random observations. I'd be really happy if like you guys can make, like, tell me a pair of angles that are just randomly equal, just because you noticed, or like you can apply the result we proved before, on these pair of angles. Throw some equal angles at me. Yeah, so exactly, right? Like, I think the proof of this definitely has something to do with, ooh, okay, 90 degrees one. It does have something to do with triangles. It's not necessarily a 90-degree triangle, a right angle triangle. Yeah, but definitely has something to do with the triangle. Yeah, Kinsley, did you have your hand up?
See if you prove ADC and ABC are 90 degrees.
Okay, so no, that is not ADC and ABC. Okay, so that is not necessarily true. They're not necessarily 90 degrees. And I think this diagram is a little bit misleading because AC looks like a diameter. It doesn't have to be. I could draw another diagram for you guys that might look a little bit less deceiving. Um, okay, like something like this. Say we have circle. Oh, so circle, and then this would also be a cyclic quadrilateral. Uh, right, and we can clearly tell that we don't have any 90 degrees in here. But oh gosh. Um, okay, this is really bad diagram. say we have it like this. And I think it's a really good idea for this problem just to draw in the diagonals. Because it does help. But A, B, C, D. What are some equal angles you guys can observe? Just like pairs of equal angles that are from the same arc.
ADC and
A,
ACD.
A, C, D. Okay. So, sorry, what, ADC?
ADC and ABC.
Ah, okay. That is not necessarily true because, oh, okay. I do have to clarify. Um, for the angles on the same arc, for them to be equal, they have to be on the same side of the arc. Like, it can't be on the arc itself, right? So, say if we're taking AC as the arc, if we're taking AC as the arc, and we're taking the short edge of um the AC arc, then this angle is subtended by this arc, right? But but for this angle over here in red, so I'm talking about ABC would be subtended by this arc, but ADC would be subtended by this arc. So they're not actually the same arc. For angles to be equal, and subtended by the same arc, they really do have to be on the same side of the arc. So, this would mean these two are subtended by on the same arc, right? So the two green angles would be equal, but the green and the red angle would not necessarily be equal. So, just be careful when we're talking about arc, we're not talking about the line it's from, right? Because both angles are from the line AC. We're more talking about the arc. So the arc AC, there's a short arc and there's a longer arc in this case, right? So they would be defined as two separate arcs, and they would not be, the angles subtended on either one of those would not be considered the same, right? So just got to be careful with that. But I can definitely see where you are going, maybe with that idea. So the two angles would not actually be equal, but what are some other ones? What are some other angles that might be equal? Pairs of angles that are from the same arc. So like literally from like the same line and on the same side of the line. Anyone you can observe? So I might take, for example, like AD. What are the angles subtended by the arc AD? So angle C equals angle D. Ooh, okay. Yeah, so usually when we're referring to angles, yes, in some cases you can refer to them as a single letter. Just because I've actually labeled the vertices, let's try like the three-letter form. So yeah, in this case, ABD and ACD would both be angles subtended on the arc AD, right? And from a former condition, we've been sort of able to say that, okay, if there's a would be able to say that ABC, I mean ABD and ABD, sorry, and angle ACD are actually equal, right? Because they're subtended from the same arc. Okay, now let's try doing this, but let me think. The arc here. What about this arc? DC. What angles are on the same one? Feel free to just, okay, yeah, so exactly, right? So angle DAC and DBC, they would also be equal because they're subtended by the same arc and they're on the same circle, right? So angle DAC should be equal to angle DBC, right? So now after we have these two conditions, we just know that ABC is equal to angle ABD plus angle DBC, right? Does everyone see that? Why ABC is equal to ABD and DBC? BAC and yes, exactly. BAC and BDC would also be equal. Yes, exactly. But I'm just pointing out the fact that angle ABC is going to be equal to ABD plus DBC. And I think that's pretty clear just from the diagram itself that this big angle is the sum of the little angles. So if we take these two facts, then we also know that, so we know this is true. We also know these two conditions are true. So we could actually change out, say, ABC would actually have to also be equal to ACD plus DAC, right? This is because ABD we can change out for ABD, we know is equal to ACD, right? So we can change ABD out for ACD. And we also know that DBC is going to be equal to DAC from this condition, right? So we can change out that for DAC, right? So that just basically means that we're able to, instead of thinking this big angle over here, ABC, we can think about it as two little angles added together. And it would be this angle, this red angle, and this green angle added together would also be the same size as angle ABC, right? Okay, so yes, that is something we also know. But if we're looking at this triangle, is there anything anybody can tell me about? If we're looking at the triangle ADC, and we know that the interior angle should sum to 180. So what is another way to express the sum of these two angles? That uses the fact that in angle ADC, the interior angle sum to 180. Anyone? Yeah, exactly. Exactly, right? So we know that the sum of the angles should be 180, and the only other angle that we haven't included within this sum is ADC, right? So it would actually be equal 180 minus ADC. Okay, so that would mean ABC is equal to 180 degrees minus ADC, right? Okay, now we can sort of rearrange our equation and we get the fact that ABC plus ADC is going to be equal to 180, right? So that sort of proves the fact that in a cyclic quadrilateral, the opposite angles, whichever pair we pick, it doesn't really matter. They just have to be the opposite angles. So in this case, we chose ABC and ADC. Well, they have to be supplementary and they have to add to 180. So we've sort of been able to prove that. Does that make sense to everyone? Yes, no, maybe? Let me know if you have any questions about anything. Okay, so Kinsley says yes. Anyone else? Anyone else have like any questions they have or feel free to let me know. Um, okay. I'm not getting anything. Um, I'm not getting any questions. I'm gonna take it that everyone understands. Okay, cool. I think we have unfortunately run a bit out of time. I will, however, try to run this a little bit, because we only do just have one more slide. So a tangent. Does everyone know what a tangent is? Or like what tangents are? Okay, yeah, exactly right. Like it's sort of like a kind of situation where you might not know the formal definition, but the formal definition of a tangent with like just in general, a tangent to a curve at a given point is a straight line which just touches the curve, right? So if we look at this diagram, we sort of see the blue curve and its tangent line would be the red line, right? Because it touches this curve at just a single point, right? And it would mean that the gradient of the tangent, which is like the slope of our tangent line, is actually also the gradient of our curve at, I guess, this particular point. Right. So that's sort of more formal definition. If we're usually in geometry or Euclidean geometry, we're usually just thinking about a line and like a tangent in terms of a circle. So a tangent of a circle would be a line that touches the circle at a single point, right? So you can imagine for like lines, usually they might just like cross, if you draw a random line, it's quite likely that it will cross your circle at 2 points, right? But for a tangent, or for the line to be a tangent, you can see AB here is going to be tangent to our circle because it only touches our circle at one singular point, which is C, right? I could draw another one, and this would not be a tangent line, this would not be a tangent line, but this, if I can get it to go, okay, it's a little bit hard to control, but this would be a tangent line because it touches it at 1 point. Okay, so does that make a little bit more sense? Kinsley, go ahead.
Are OCB and OCA always 90 degrees?
Yeah, exactly. Right. So the one condition that I was gonna mention to do with sort of tangents to circles is that if we take the point where our tangent line just touches our circle, and we sort of draw a line from this point to our center, it's an interesting property that both of these angles would be 90 degrees, right? It just touches, and then it would also just touch at a 90 degrees. We can talk about the reason for this next session. And I also do want to talk a little bit more about cyclic quadrilaterals next lesson as well. Some properties to do with those. But I think for now we have run out of time, so I don't want to hold anyone back. But in the meantime, if anyone has any questions, feel free to email us. I know I think David has sent some work through. I'm going through that now.